everyone. Oh, look at all these faces. That's so nice. Thanks for having your cameras on. Sorry, I'm a couple minutes late. The stupid painters came in and they painted on like with these really thick brush strokes. So now there's going to be this one pot. Everywhere else is rolled and with this other texture. Now they got a different texture. So I'm kind of fighting with the painters and I'm feeling grouchy. But you know what? Math's going to make me feel better. So let's do some math. Who's got any comments, questions, concerns? I think one of your problems last night, I tried to look through, but I missed one. I think one of your problems last night needed the root test. It was number 34. If you got it wrong, I don't care. It's not going to be counted, but I'm sorry that you did it if it was stressful. But it's going to be, it won't count against you. It'll just maybe have spent some of your time. Anything anyone wants to ask about or? Okay, all right, let's get back to where we were. All right, let me share my screen. Okay, so I've just written a bunch of stuff that we already had from last class, and you don't have to rewrite it, it's already in your notes, but I wanted to start where that was. Hold on, there might be, let me open the chat again, maybe there's another chat. Right. Yeah, if you just skip 34, that's totally fine. It's not going to be counted either way. Sorry if you wasted your time on it, but it's not going to count against you. All right, so okay, here's the example that we did last class. I just wanted to sort of quickly review where we were. So we had this power series. Remember a power series, it's kind of like a brand new series for every single, oh my God, the workers are here. Can you just hold on one second? I'm sorry. All right, so here's where we were. We have these power series, and remember a power series is just like a brand new series for each value of x. And there's a value of x for each real number. So there's infinitely many series hidden in a power series. Anytime you plug in a value for x, you get a brand new series. And so then the question for power series is, for what x values do those, if you plug in an x value, does it converge? Does it diverge? And which of the x values are you sure that it converges for? So the way we were trying to do this last time is we took our power series and we used the ratio test. So this is what happened when we did the ratio test. I don't have all the details, but you have it in your notes. So when we did the ratio test, you know, the limit that we got is absolute value of x minus 3. And we remember from the ratio test that when the limit's less than 1, the series converges absolutely. When it's greater than 1, it diverges. So we figured out when each of those were. And when it is less than 1, that's going to be when x is in this range between 2 and 4. When it's bigger than 1, it diverges. And I got screwed up with the calculations last time. I got confused myself. I should have put a plus here instead of a minus. And if you solve that, you see that it's, well, when it's bigger than 4 or less than 2, that's where it diverges. And the last thing from the ratio test is that when L is 0, then there's no information. And so that's at 4 and at 2. So here's like putting everything together. This is what we've found so far, is that in this region, for all these x values between 2 and 4, it converges absolutely. If x is bigger than 4 or if it's smaller than 2, it diverges. And right at these two places, when L is 1, we don't have any information at all. Okay, so that's just catching up to where we were before. Does anyone want to ask a question about this catch up before we go forward? We're good? All right, so we almost know all the answers. We almost know exactly where this thing converges and diverges, but we don't know about two values. So we have to check those two values separately. Those are the endpoints of this interval. So we have to check the endpoints of this interval separately. So I guess, let's see, if I'm going to color code things, this is where it diverges. And these are the question places. So let's check those values separately. So you have to check the endpoints. So one of the endpoints is x equals 4. So we just go right back up to the power series and we plug in 4 everywhere we see an x. So I'm going to repeat this power series down below. So this power series is n equals 0 to infinity, x minus 3 to the nth power over n. And if I plug in 4, when I see an x, I've got 4 minus 3 to the n. I should be doing this down. Let's move this. It's easier to read when, oops, where'd it go? It's easier to read when computations go down. And that's just 1 over n. What does that do? Does that converge or diverge?
Diverges.
You probably said, and that maybe my volume's not high enough. Could you say that again, Will?
It diverges
Yeah, that's right. Why is that?
because n approaches infinity.
Okay, so it does approach infinity, but to answer why, we have to give maybe a test or other reasons. So
it has to be p is greater than 1 and it's equal to 1, so it's going to diverge.
yeah, that's right. So it does diverge and it adds up to infinity, and then our justification for that is that it's a p series because it's a p series with p equal to 1, and that's when it diverges. Okay. All right, so we checked that endpoint. Let's check the other endpoint, x equals 2. Okay, so that's -1 to the n over n. In fact, it's -1 to the n times 1 over n. What's the name of this series? We've seen this series before. What do we call it?
Alternating?
Yeah, alternating. It's alternating, but it's specifically, it's the alternating harmonic series. This one just happens, this one when n is 1, this is the plain old harmonic series. Sorry, when p is 1, and then this is the alternating harmonic series. And we did this in an earlier example. In section 8.4, and found that it converges. So I'm not going to do that same problem again. We have it in our notes. Okay, so it converges here and diverges here. So if I want to talk about where does it converge, the answer to where it converges when x is in, so on this interval, let's say it that way. We include 2, and we go all the way up to 4, but we don't include 4. So it converges for every x in that interval, and it diverges everywhere else. All right, so there's one example of what can happen. You know, this took a lot of steps, but none of the steps were too hard for us. There's just a lot of steps. So we just do the steps one at a time. These steps right here, in the future, we don't have to do these. I was doing it right now just to sort of point out what's going to happen, but it's always going to sort of converge absolutely in some region, diverge outside the region, and then we don't know on the boundary. So we don't really, these two parts, we're not going to have to check these in the future. Okay, I want to do two more examples. So that was our first example. Here comes another one, example 2. How about this series? From 0 to infinity of x to the n over n factorial. Same thing, we want to know which x values does this series converge at. So which x values does it even make sense to think about this series? And which x values does the series not even make a finite sum, so it doesn't even make sense to think about? So we're going to use the ratio test. So limit as n goes to infinity of absolute a sub n plus 1 over a sub n. Okay, if I do a sub n plus 1, that's going to be x to the n plus 1 over n plus 1 factorial. Then instead of, just like we've been doing, instead of dividing by a sub n, I'm going to multiply by the reciprocal. So that's going to be times n factorial over x to the n. So this is going to cancel. So this cancels with here, and I just get an x. What do I do with the factorials?
You can change the bottom one and then the n factorials will cancel out.
Yeah, that's right. So I'm going to, instead of n plus 1 factorial, I'm going to write that that's n plus 1 times n factorial. And then those n factorials cancel out. So this is what we did in last class. We can do it again now. X is just a constant. X isn't, I mean, X is a variable in general. But if you're just thinking about it for an individual x's, n is changing. N doesn't have anything to do with x, so I can pull x out of the limit. What's that limit? Can you tell?
0.
Yeah, limit's going to be 0. So I've got x times 0, so that's just 0. So that's what our L is. What does the ratio test say? When L is 0, what do we know?
It converges since it's less than 1.
Yeah, that's right. It converges since less than 1. So the thing that we care about is that it's less than 1. It converges, but we're supposed to be asking a question about x values. So for what x values does this converge? So we know that series using the ratio test. Series converge when L is less than 1. But our original question was for which x values?
It would be for all values where L is less than 1. So
Yeah, and for what values are L less than 1?
Any value of x.
Yeah, I think that's right. For every value of x, it's going to be that way. Yep. X didn't even play into it, right? I don't care what number you put here, 342, you're still going to get that thing times 0. You're still going to get limit less than 1. Okay, so in fact, the answer is every value of x. Answer is all values of x. So all x in all the reals. Okay, so that happens sometimes. Sometimes you get this interval. Sometimes it converges everywhere. Look at one more thing that can happen. Here's another example. Here's one, n equals 0 to infinity. N factorial times n minus 5, oh, sorry, x minus 5 to the n. Same thing. So I want a sub n plus 1 over a sub n. A sub n plus 1 is just n plus 1 factorial times x minus 5 to the n plus 1 power. A sub n is n factorial times x minus 5 to the nth power. And the stuff cancels, the usual stuff cancels. So that thing cancels with that. I'm going to get let's see, I don't need the absolute values on the n's because the n's are always positive. I do still need it on the x minus 5s. So I'm going to get n minus 1 factorial. Oh, n plus 1 factorial over n factorial times absolute value x minus 5. Just like before, x minus 5, that's the constant, that doesn't change with n, so I can pull that out in front of the limit. And as I don't remember if it was Diego or Zane recommended, we can do that same old trick. We can write n plus 1 factorial as n plus 1 times n factorial. And then these n factorials cancel. What's this limit?
Infinity.
Yeah, it's infinity. So this thing is going towards infinity. It's getting bigger and bigger and bigger. I don't care what x is. This is just going to be a constant. Whatever x value you pick, you're going to have a number here. That number times something going towards infinity, that whole product is going to go towards infinity. So the limit is infinity. Oh boy. Okay, so what do we learn from that? Infinity is bigger than 1. So where does it converge?
Nowhere.
Close. You want to think nowhere, but there's a little bit of a calculational weirdness. So it converges almost nowhere.
At
So,
5.
yeah, at 5 it converges. Everywhere else it diverges because it's always going to converge at the center. See, this is why I was saying it's kind of a little bit of a lie, because if this diverges, you know, when x is 5, I've got a 0 times something going towards infinity. But this being 0 all the time, you know, way back in here, this being 0 all the time, I'm just taking the limit of 0. The answer is going to be 0. So the only place it converges is x equals 5 at the center. Diverges everywhere else. Okay, these are the 3 things that can happen. So power series are always going to converge somewhere. They're always going to converge at the center. And the 3 things that can happen are either it just converges at the center and that's it, or it converges in some interval around the center, or it converges everywhere. Those are the 3 things you get. Okay, and we had all 3 of these cases. So this first thing that we thought of, in fact, look, here's the center. The center was at 3, and it was in the center of this interval. Here it converged everywhere. Here it converged only at the center. Okay, those are the 3 options. So so all that is to lead us towards radius of convergence. So Here's a theorem about that. Okay, theorem says this. For a given power series, there's only 3 different things that can happen. So let's call the power series. You know, here are the coefficients, and then I have x minus a to the n power. There are only 3 possibilities. First of all, the series only converges at the center, and that's it. Or the opposite thing, where it converges it for all x values. Or somewhere in the middle. Here's the middle situation. And I like this picture right here because see right here, this is the thing that we were calling the center. And it's at the center of the interval where it converges. So that's the reason for the choice of word center that we've been using. Okay. So the last thing is there's some interval that it converges on. That interval is around the center. So there's a positive number r. So that the series converges if distance between x and a is less than r, and it diverges if the distance between x and a is greater than r. Notice how nothing was said here about the distance between x and a equaling r, because that's the case where the ratio test doesn't work. So that's the case where we have to check individually, just like we did in the first example today. So in this case, this r is called the radius of convergence. So let me just give you that as a definition. Okay, I won't separate it actually, because I'll have to say all this stuff. So let's just say in this case, yeah, okay, r is called the radius of convergence. At the center. I mean, if you had a circle, if we were in 2 dimensions, you'd have the center, and then you could sort of go out a certain distance in all directions. That would be your radius until you sort of hit this edge. Well, now if you're on the line, it's the same idea. You've got this center, and then you've got the radius. You can go that distance in either direction and still be in the region of convergence. But once you escape that radius, it diverges. Okay, so that's the radius of convergence. There's also something called the interval of convergence. So the interval of values x on which the power series converges. It's called the interval of convergence. of the power series. Okay, so right here, this was the interval of convergence. Closed interval on this side, open interval on this side. It's the interval of values on which it converged. Yeah, the interval of convergence, it's sort of an infinite sized interval. It covers the entire real line. So here, R is the interval of convergence. And here, it was just the number 5. It doesn't really seem like an interval. It's a sort of an interval of size 0. You're just at the origin only. I mean, you're just at the center only. So it's weird to call it an interval, but we do. Okay, so those are the 3 things that can happen. That's it. The difference between asking for the radius of convergence and asking for the interval of convergence is the radius of convergence, you don't have to answer what happens at the endpoints, right? The radius of convergence, you just have to say inside converges, outside diverges, and nobody asks about the endpoints. If you asked about the interval of convergence, then you also have to know what happens at the endpoints too. Are they included? Are they not included? That's sort of the difference. Okay, so we've done 3 problems. Would you like to try one on your own now, or do you want us to do one more together? How you feeling?
Can we do one more?
Yeah, absolutely. Okay, so I got one more. How about, this is a good one. How about this example? Let's try here. So find the radius and interval of convergence. For this series. Square root of n plus 1. All right, well, it's power series. And so I just launched into using the ratio test, which you'll always want to use. But one reason that it makes sense to launch into using the ratio test is the ratio test we can always use. It doesn't need all positive terms. It doesn't need alternating. It doesn't need any of the conditions. You can just go into it. So we don't care what the series is doing. If sometimes it's alternating, that's fine. In fact, there'll always be places where it's alternating. So we're safe to use the ratio test for these power series. And so that's what we're doing. So let's do that again. Here we go. Use the ratio test. All right, let's see. So we want to take the limit as n goes to infinity of absolute a n plus 1 over a n. All right, a n plus 1. So negative 3 to the n plus 1, x to the n plus 1 over n plus 1 plus 1, so that's square root of n plus 2. Then we're going to multiply by the reciprocal of a sub n, so I'm going to have a square root of n plus 1 on the top. And negative 3 to the n, x to the n. All right, let's see, some stuff's going to cancel. So this goes away, and I'm just going to give an x. This goes away, and I'm going to get a negative 3. I can take away the absolute values on the square roots of the n plus 1s, but I have to keep it on the x. So if I put all this together, what am I going to get? I'm going to get an absolute value -3x. And then I'm going to get times square root of n plus 1 over square root of n plus 2. Are there any questions about this? All right, so, just like we've done before, the x is a constant, and I can in fact pull the -3 out of the absolute value, so I just get a 3 absolute x. And then I can put these together in one square root sign. How can I figure out this limit?
Multiplying by the reciprocal of the highest power.
Yeah, that's right. And I'm just going to do that inside the square root sign, but that's exactly what we do. So I'm going to just multiply this by 1 over n and this by 1 over n. Okay, so when I distribute, I'm going to get a 1 plus 1 over n over 1 plus 2 over n. So in the limit, I have 3 absolute x times, that limit is 1. Okay, so by the ratio test, we know that the series converges when the limit is less than 1. So what's the limit? So I've got 3 absolute x has to be less than 1. So absolute x is less than a third. Is this centered at? Okay, let's see. All right, so what's the radius of convergence? We look back here at the definition, the radius of convergence, that's the number so that when you're less than that number, you converge, and when you're bigger than that number, you diverge. So what is it in this case?
It would be the absolute value of x minus 1/3.
Actually, so we wouldn't include x in it because, so we're sort of asking from the center 0, how far can we go out before, how far can x change? So x isn't going to be a constant in this part, but how far we can go away is a third. So the radius is going to be 1/3. If we think about what this looks like, so absolute value x is a third. If I think about the number line, here's 0, here's a third, here's negative a third. So we're saying that it converges inside here. Here's the center. So the radius of convergence, how far can you get away from the center? 1/3 in either direction. So that's what the radius is. The interval of convergence, we don't quite know yet, right? Because we don't know what happens at those endpoints. Maybe those endpoints are included in what converges and maybe they're not. We just don't know. So to find the interval of convergence, we have to check the endpoints. Oops. So here's the endpoints, negative a third and a third. You can see them right here. So we check them one at a time. What's our series? Oh, here it is. So negative 3 to the n, x to the n, square root of n plus 1. If I plug in negative a third, so I've got negative 3 to the n times negative a third to the n over square root of n plus 1. I can combine those and I've got negative 3 times negative a third. That's just 1. I've got 1 to the n. Does that converge or diverge? How could we tell?
Diverges
Yeah, you're right. Why do you think that's true?
since it's less than 1.
Yeah, it's like a p-series. So it's not a p-series, but it's like a p-series. So we'd have to use the comparison test or the limit comparison test. So which one? Let's use the limit comparison test. So suspect diverges. Use limit comparison test to compare. What do we want to compare it to? What's the p-series that's nearby? It's 1 over n to the what power?
1/2.
Yeah, 1/2. Good. Okay, so so first of all, what does that series do? So n equals 0 to infinity, 1 over n to the 1/2 is a p-series with p is 1/2. The important part is that that is less than or equal to 1, so it diverges. And now, what else do I need to use the limit comparison test? There's a condition. What's the condition?
Positive
Yeah,
on the range.
yeah, that's right. So both of them have to be all positive terms. So so condition positive. But let's see, this series 1 over square root of n plus 1 and the series 1 over n to the 1/2, they have all positive terms because n's always positive, or 0. We better not start at 0. Let's start at 1. We know the convergence doesn't matter where we start. And I'm afraid if we start at 0, we're going to take this 1 over 0, and that's not good. So have all positive terms. So we can use the limit comparison test. I wonder if I can move that. Oh, that looks okay. Okay, so the first thing is we know what the thing we're comparing it to does, and then now let's take the limit. Who do we put on the top? The thing that we know or the thing that we don't know?
The unknown goes on top.
Yeah, thanks. The unknown goes on top. So we're gonna put 1 over square root of n plus 1 here. And then the thing that we know, which is 1 over square root of n. And then take the limit. Instead of a fraction, I'm just going to multiply by the reciprocal like we've been doing. And then we've already done this kind of stuff earlier. We're just going to multiply top and bottom by, divide top and bottom by the highest power of n. Now we can take the limit. Square root of 1, which is 1. What if the limit's 1? Does that mean there's no info? What does limit 1 mean for the limit comparison test?
Doesn't it converge at 1?
For the limit comparison test, if you get a number, if you get a constant between 0 and infinity, not including 0, then they both do the same thing. And since the one we know about diverges, that means we want the one we don't know about also diverges. So by limit comparison test, both series converge or both series diverge. And since the original one diverges, that means the other one diverges too. Not the original, but since the one we know about. Okay, so what that means is, we don't get to include this guy, x equals negative 1/3. No, diverges, doesn't converge there. But there's still more to check. There's still positive 1/3. Right, what's the original series again? Here it is. So I'm going to plug positive 1/3 whenever I see an x. Okay, well, since those are both to the n power, probably be nicer if I wrote it this way. I can put them both inside the same parentheses, and I get -3 times 1/3. It's going to be -1 to the n power. What kind of series is that?
Alternating harmonic?
It's alternating. Oh, it's almost harmonic, but the harmonic is only when it's got a plain old n in the bottom. So this is alternating, not harmonic. It's an alternating piece. It's not even a piece series. It's just alternating, I guess. So our only test really is alternating series test. You might think, well, why don't we use the ratio test? Because the ratio test we can use when we don't have positive terms. The answer is, if you did use the ratio test, you would get 1 and no information, because that's how we got x equals 1/3 in the first place, right? We're testing that because the ratio test didn't give us any information. So it wouldn't make sense to use the ratio test here. We'll still get no information. So the only thing we can do right here is we're going to use alternating series test. What are the things that we check?
Decreasing?
Yeah, that's right. So we pull away the alternating part from the, let's do that right now. So I've got -1 to the n, that's the alternating part. I pull that away from the positive part. And b sub n is that positive part. And we have to check decreasing. Well, what we really want is b sub n plus 1 to be less than or equal to b sub n. There's ways you can do it. We can take the derivatives, if we can treat it as a function and take the derivatives, or we can just sort of on the side, we won't include this, but we see what is b sub n plus 1 is going to be 1 over the square root of n plus 2. So how can I compare these? Let's see. I know that n plus 1 is smaller than n plus 2. So I'm starting somewhere where I think everybody's going to believe in. I think we can all believe that n plus 1 is less than n plus 2. And that means that the square root of n plus 1 is less than the square root of n plus 2. Why is that true? There's a word that I'm looking for. Why is it, just because n plus 1 is smaller than n plus 2, why is it true that the square root of n plus 1 is less than or equal to the square root of n plus 2? Does anybody know? It's a property of the square root function.
Oh, because n is equal to or greater than 1.
N is
Or
bigger.
is there-
Let's see. No, I mean that will matter, but because generally you can't take the square root if it's much less than that. But in fact, there'll be some functions, there'll be some places where where n is bigger than or equal to 1, and still this trick doesn't work. So let me just point out something to you. Here's something that I think you haven't thought of before, for good reason. So most of your life you've spent with equalities, and you're pretty good at solving equalities. You know the rules, the things that you can do. You know that if you take the square root of both sides, if you start out equal, then you end up equal. If you take tangent of both sides, if you start out equal, you end up equal. You know the things that you can do to solve these equations. You don't have very much intuition with inequalities just because you haven't really had a lot of experience with it. This hasn't been the sort of thing that you've been doing since you were a kid. And they don't work like equalities, but by default, you're going to want to treat it that way because that's the thing that you know, right? So this is a chance to make a mistake by trying to apply things that work for equalities to other situations. So the reason this works is because square root is an increasing function. And I'm going to talk about that for a second. Okay, so if I had a function that was decreasing, if a was less than b, oops, that's supposed to be a b. If a was less than b, then f of a would be bigger than f of b. Does that make sense? So it's not always true that if f of a is less than, if a is less than b, then that doesn't necessarily mean that f of a is less than f of b. It doesn't mean that you can apply any function that you want and the inequality still works. It's only true because in this special case, the function is increasing. And if you remember the definition, oh, that's not really increasing. If you remember the definition of increasing function, the definition of increasing function was if m is less than n, then f of m less than f of n. Do you remember that definition from like a million years ago before you even learned, before you were taking the derivatives in calculus? Okay, so that's why it works, because it's an increasing function. If you had a function that wasn't increasing, then you wouldn't be able to do this thing that we just did. Okay, time's almost up, but taking reciprocals is going to switch the order. If I have a smaller denominator, then I have a bigger fraction. And that means b sub n is bigger than b sub n plus 1, so decreasing. Second thing to check is the limit. So limit as n goes to infinity of b sub n. B sub n is 1 over the square root of n plus 1. And we already decided that limit is 0, and that's the thing that we want. So by the alternating series test, this series converges. All right, so what do we get? The interval of convergence includes a third. It doesn't include negative a third. Includes a third, doesn't include negative a third. All right, you know everything you need in order to do the homework, and I'm going to give you an extra day. But here's what that means. It's possible that you'll have 2 assignments due Tuesday, but that seems better than cramming one in now and then having the next one for Tuesday. If you want to turn one in now, you can, but you have extra time if you want to. So section 8, what is this, 8.5 will be due Tuesday. And section 8.6 might be due Tuesday. Or else it'll be due Wednesday. So tomorrow we're going to do, we'll give you a classwork and you'll work on an example from 8.5 together. Then we'll all feel like we're ready to move on with our lives and we'll go to 8.6. All right. You did it. Good to see everyone. Are there any questions? Okay. I'll see you later. Bye.
Thank you.
Thank you, Professor.